Welcome back to our channel where we dive deep into the world of AI, machine learning, and data science. I'm Alistair Louise, and in today's video, we will explore how to solve Kaggle's house prices dataset while focusing on explainable AI concepts using SHAP values. We'll go through how to interpret model predictions and make them understandable. Let's get started. Before we dive into the code, let's take some time to understand the theory behind SHAP values. SHAP stands for SHapley Additive Explanations, a powerful method for explaining individual predictions made by machine learning models. This method is rooted in cooperative game theory, which was developed by Lloyd Shapley in the mid-20th century. In cooperative game theory, the Shapley value is used to distribute the total gains to players based on their contributions. When we apply this concept to machine learning, each feature in a dataset can be seen as a player in the game, and the prediction made by the model is the payout that needs to be distributed among these players. The goal of SHAP is to fairly attribute the payout, that is the prediction, to each feature based on its contribution. This is achieved by considering all possible combinations of features and calculating the marginal contribution of each feature to the prediction. Mathematically, the Shapley value for a feature is the average marginal contribution of that feature over all possible combinations of features. One of the fundamental properties of Shapley values is their additive nature. This means that the sum of the SHAP values of all the input features equals the difference between the baseline model output, that is the expected value, and the actual model output, for the prediction being explained. This property ensures that SHAP values provide a consistent and intuitive way to explain individual predictions. Let's break down the additive property with an example. Suppose we have a model that predicts house prices. The baseline model output, which is the average prediction across all houses in our dataset, might be $200,000. If the model predicts that a particular house is worth $250,000, the SHAP values of the features for this house will sum up to $50,000, which is the difference between the baseline and the actual prediction. This helps us understand how much each feature contributed to the difference from the average prediction. Another key aspect of SHAP values is that they provide both global and local explanations. Global explanations helps us understand the overall importance of features across all predictions made by the model, while local explanations help us understand the contribution of each feature to a specific prediction. This dual capability makes SHAP a versatile tool for model interpretability. The SHAP method is model agnostic, meaning it can be applied to any machine learning model, whether it's a linear model, a decision tree, or a deep neural network. This flexibility is achieved through different SHAP algorithms like kernel SHAP, which is a model agnostic method, and tree SHAP, which is optimized for tree-based models. To summarize, SHAP values provide a clear and consistent way to interpret the predictions of machine learning models by fairly distributing the prediction to the features based on their contributions. This not only helps in understanding how the model makes decisions, but also in building trust and transparency in AI systems. Now that we have a theoretical understanding, let's move on to a practical example. We'll use the house prices dataset from Kaggle and an XGBoost model. We'll demonstrate how to use SHAP values to interpret the model's predictions. First, we import the essential libraries: Pandas for data manipulation, NumPy for numerical operations, XGBoost for our model, and SHAP for SHAP values. We also import train test split for splitting the data and label encoder for encoding the categorical variables. We then load the dataset and separate the features X from the target variable Y. Let's also visualize the train dataset by displaying the first row using the Pandas head function. Next, we need to encode the categorical features before training our model. Here, we loop through each column in the dataset that has a data type of object, which indicates a categorical feature, and use label encoder to convert these categorical values into numeric values. Next, we split the data into training and testing sets. Here, we split the dataset into training and testing sets using an 80-20 split and a random state for reproducibility. We then initialize and train a basic XGBoost regressor with 100 estimators with a max depth of 3 and a learning rate of 0.1. Now with our trained model ready, let's explain the model's predictions using SHAP values. We initialize a SHAP explainer with our trained model and the training data. The explainer computes the SHAP values for the test data. To visualize the importance of each feature, we can create a summary plot. Let's take a closer look at the SHAP summary plot we generated. This plot is a powerful visualization tool that summarizes the impact of all features on the model's predictions across all samples in our dataset. The features are listed on the y-axis, ranked by their importance, meaning the higher a feature is on the y-axis, the more it contributes to the model's predictions. The x-axis represents the SHAP values, indicating how much a feature pushes the prediction away from the baseline. Positive SHAP values push the prediction higher, while negative values push it lower. Each dot on the plot represents a SHAP value for a feature for a specific sample. The color of the dot indicates the value of the feature for that sample, with red indicating high feature values and blue indicating low feature values. For example, if a high feature value pushes the prediction higher, you will see red dots clustered on the right side of the plot for that feature. From the plot, we observe that overall quality is the most important feature in predicting house prices, as higher quality homes tend to have higher prices. Similarly, GR live area shows that greater living area increases the predicted house price. Total basement square feet also significantly impacts predictions, with larger basements pushing the price higher. On the other hand, overall condition shows a more complex relationship where higher values do not always push the prices higher. By examining this plot, we gain a comprehensive understanding of how each feature impacts the model's predictions. This not only helps in interpreting individual model predictions, but also provides insights into the overall behavior of the model. We can see which features have the most substantial effect on the predicted house prices and how changes in these features can alter the predictions. Let's also look at a specific prediction using a waterfall plot. The waterfall plot visualizes how each feature contributes to a specific prediction. It starts from the baseline value and adds the contribution of each feature step by step until it reaches the model's prediction. The waterfall plot is another powerful visualization that helps us understand how different features contribute to a specific prediction. The plot starts with the baseline value, which is the average prediction made by the model across the entire training dataset. This baseline value represents the expected prediction if we had no information about the specific instance. In our waterfall plot, the baseline value E of f of x is around $175,381. From this starting point, we add or subtract the SHAP values of each feature to understand how they influence the final prediction for this particular house. For this specific instance, the features GR live area and overall quality significantly decrease the predicted house price by around $14,662 and $12,943 respectively. This means that for this house, the large living area and the high overall quality lead to a lower predicted price, which could be due to specific market conditions or other interactions captured by the model. On the other hand, features like overall condition, your remodeling addition, and garage finish increase the predicted house price. Overall condition adds about $5,123 to the prediction, indicating that a better overall condition of the house positively impacts its price. The waterfall plot clearly shows how each feature contributes to the final prediction. Positive SHAP values, marked in red, indicate features that push the prediction higher, while negative SHAP values, marked in blue, indicate features that push the prediction lower. The plot visually walks us from the baseline prediction to the model's final output for this instance, providing a transparent view of the model's decision-making process. By examining this plot, we can see the combined effect of all features on the predicted house price, allowing us to understand the key factors driving the prediction. This level of detail is crucial for building trust in the model and making informed decisions based on its outputs. In this video, we explored the fascinating world of explainable AI by diving deep into SHAP values. We started with a theoretical foundation, understanding how SHAP values derived from game theory provide a consistent and fair way to explain model predictions. We then applied these concepts to Kaggle's house prices dataset using an XGBoost model. We demonstrated how to encode categorical features, train the model, and compute SHAP values. Through visualizations like the SHAP summary plot and the waterfall plot, we gained insights into how individual features and their combinations influence the model's predictions. This not only helps in interpreting individual predictions, but also provides a broader understanding of the model's behavior, enhancing transparency and trustworthiness. If you found this video helpful, Please give it a thumbs up, share it with your friends, and subscribe to our channel for more AI, ML, and data science tutorials. For those who prefer reading, we have also prepared a detailed written blog that accompanies this video, providing all the explanations and code snippets discussed here. You can find the link to the blog in the description below. With that being said, thank you for watching and see you in the next video.